Okay, so I think we'll probably get started. So thanks all for coming to the latest Value in Energy Data seminar series talks. I'm very excited for today's. Just a little bit of housekeeping first. So remember, this is being recorded. We'll have this on our YouTube channel shortly after the event. Everyone turn off their microphones, please, and their videos, so that during when the speakers are speaking, they'll be the focus of the video, and the slides will be. And if there's any questions, then please leave them in the chat throughout. We'll get to them at the end of the session. So just before I introduce the speakers, as you'll notice, there was 2 speakers today, so there's a slight adjustment, but the main talk is Zoya will be talking on digitalization in energy systems. But we're happy to also have her PhD student, Mohammed, who'll be talking a bit about some data science as well. So without further ado, let me introduce them both. I'm very excited to have Dr. Pourmirza, who is the lead of the Security and Resilience team at the Centre for Energy at Newcastle. She works with the National Centre for Energy Systems Integration and the Active Building Centre as well. She's investigating energy systems digitalization with a focus on ICT design, data communications efficiency, and cybersecurity. She's currently a principal investigator for the Energy Systems Digitalization Project, and also PI for the EPSRC IAA project, Digitalization and Digital Twinning of Energy Systems, which is a collaboration with ourselves. Mohammed Khalil is a PhD student at Newcastle University in the School of Engineering, and also a member of Newcastle University's Artificial Intelligence Lab. He's got a background in the area of computer science in engineering, and his research interests fall into machine learning, deep learning, data analysis, and time series forecasting, and has a particular focus on applications in building energy management systems. So without further ado, it's my pleasure to introduce Zoya, who will give the first part of the talk.
Thanks, Steve. Let me share my screen first. All right, so can you see my screen?
Yeah, looks great.
Okay, thank you. So hi, everyone, and it's lovely to be here, and thank you, Steve, for the invitation. Today, I'm going to talk about issues around energy system digitalization, the opportunities they offer, the current challenges, the solution, how to tackle these challenges. I will also present some of our projects at Newcastle University, discuss our findings. I will talk about some of these projects briefly, and then I will talk about some of the projects in more detail that I think that might be interesting for you. As we all know, UK government committed to achieving net zero carbon emission by 2050, and this was compared to the previous target of an 80% reduction in emission by 2050. So to achieve this goal, we have 3 pillars, which are decarbonisation, decentralisation, and digitalisation. And we think that digitalisation would refer to integration of various parts of energy system with technologies such as Internet of Things, artificial intelligence, digital twin, and distributed ledger technology. And also we think that this technology can make energy system to become more connected, sustainable, and reliable. And they can support data analysis, they can provide peer-to-peer energy trading, and they can also allow deeper penetration of renewable resources, and etc. So this technology can also improve energy system flexibility. And digitalization also can enable creation of innovative products and services and innovative business models like heat as a service that we will discuss later in this webinar. Okay, so we know that part of this digitalization can provide some opportunities, but at the same time, this digitalization can offer some challenges for our energy system. Some of the technical challenges are around data, for example, challenge around limited data availability, lack of data governance and interoperability, lack of standards for data, issues around missing data, and also issues around how to handle large volume of data for storage, for transmission, etc. So additionally, we are facing challenges around cybersecurity and data privacy because of this digitalization. So these challenges are really important because when we are talking about smart energy system or digitalized energy system, we are usually talking about applications and products which were traditionally offline and they're becoming online now. So we need to protect these devices. We need to protect all the applications against cyber attack. Also, we need to make sure that the personal data collected by these devices are also protected as well. So you might be interested to know what would be the impact of cyber attack on energy system, right? So in case if our cyber attack, if our energy system is under cyber attack and it's compromised, then this attack can affect the energy system in various ways. For example, it can affect the capability of energy system to deliver a reliable service to consumer and can lead to cascading failure in other sectors, for example, in telecom sector or in water supply network, that they all rely on these systems to function. Now I will present some of the works that we have carried out in Newcastle University. Some of these works focus on the opportunities that digitalization would provide. For example, we had a project around heat as a service, which is a new business model that is enabled by digital technologies. Heat as a service provide consumer with an agreed heating plan rather than simply paying for units of fuel. So in this project, we organized some facilitated group discussion with key stakeholders, and we explored issues of trust between consumer and supplier, supportive policies, financing business model, and technology and data within the HASS model. Then we proposed some policy and research recommendation based on our findings. We have published our results in a journal paper, so if you are interested, I have shared the link here, or you can contact me. I can share the article with you. Another project that we are currently doing is about improving building energy management. This is a PhD project that Mohammed Khalil is doing, and he will discuss about his finding later on in this webinar. There are also another project that I was awarded to build a network around energy system digitalization with international partners. We organized 2 workshops back in November with partners from Monash University in Australia, DTU in Denmark, KU Leuven in Belgium, Siemens, and also Energy Systems Catapult, and also a number of other UK universities. We discuss about various topics in energy digitalization. The discussions were mainly around top challenges. What are the top challenges of digitalization? And the results were came as lack of skilled people in power and energy sector, and skilled people having knowledge about digital technologies in energy sector. Some other top challenges were around cybersecurity challenges and importance of data quality. We also discussed the impact of digitalization on energy by 2035 and 2050, and attendees mostly pointed to having better prediction by using AI system, and also the usefulness of digital twin technologies by that time, and also enabling better flexibility services. The recordings of these workshops are also available in YouTube, and I shared the link with you here. So if you're interested, you can go to these and listen to these workshops. Now let's go to our project that focus on challenges of digitalization. In these projects, we investigated two categories of challenges. The first category is about dealing with data challenge, like dealing with missing data and dealing with efficient data communication. The second category is about dealing with cybersecurity challenges. For the challenge around missing data, we know that we might miss data because of measurement error, malfunctioning of sensors, power outage of the sensor, or network failure. Well, all these inconsistencies in data can negatively influence the energy consumption modeling or control and management of applications. So we had a small project a few years ago that my colleague was leading on. In this work, we tried to do some initial study around the challenges around missing data treatment. We studied 8 methods of imputing missing data in building sensor data. And we wanted to find out which method is the best fit for the energy and building data set. We used real data collected from our testbed, which was Living Lab in Newcastle University. Actually, our results showed that the K nearest neighbor, KNN, can get the best results between other algorithms. Actually, this was a small experimental project, and there was some limitations to this work. For example, we used lighting variable, which is really strongly time dependent. We used data from educational building, which is only one specific type of building. So if someone is interested to follow up on this work, they can look into other parameters or investigate other types of buildings like residential buildings. So in the rest of this webinar, I'm going to talk about challenges of data communication and the techniques to solve this problem. And also then after that, I will discuss about cybersecurity challenges. And I'm going to discuss these projects in more detail and talk you through our findings and results with greater detail. One of the challenges in digital energy system is how to deal with large volume of data for transmission. In energy systems, some components, such as, let's say, for example, smart meter components or some other monitoring devices are connected via wireless communication. And they're also without the benefit of being connected to electricity supply. So data transmission would be an issue for them if they run out of batteries. So that's a big issue when we are talking about wireless communication for the devices that are running on batteries. And we know that energy consumed for transmitting 1 bit is equal to energy for processing around 1,000 instructions. So we understand that we could save huge amount of energy of these devices by minimizing the volume of data prior to data transmission. And there is another problem. And that is one of the key constraints of these devices is that they have limited resources, such as they have limited battery, they have limited processing power, they have limited memory. So we could not come up with some very complicated data reduction algorithm. So I came up with the idea to develop a new data reduction algorithm that reduces the communication energy cost while maintaining the integrity and quality of data, and while using network resources efficiently. This algorithm needs to compress data prior to data transmission and then decompress the data on the other side, which is the receiver side. And I wanted the algorithm to be lossless algorithm, so I would not lose any data while doing the compression and decompression. And I call this algorithm Draco. Draco stands for Data Reduction Algorithm for Correlated Data, and it can be applied to data with high data sampling rate and can transmit essential information with compression ratio between 70 to 99% compression efficiency, depending on the type of the data, which is really interesting for us. Now, let's see how Draco works. We collect data with high frequency from our testbed. So there was a great degree of correlation between our data because the data collection was with very high frequency. And then I look at this feature, I took this feature into account and developed a simple data reduction algorithm which used XOR gate to discard the redundant part between each two consecutive measured value and then transmit the changing part only. This changing part is usually small portion of binary representation of the whole value. And Draco, this new algorithm showed that it can improve the energy efficiency of communication network by transmitting a smaller volume of data while keeping data integrity. So keeping the data integrity was, again, one of our objectives. Next, I improved the efficiency of Draco by using the concept of run length coding, and I call this algorithm Draco 2. So in Draco 2, if any consecutive value appears as 0 after converting to binary value and after applying XOR, then Draco will only send one instance of previous value together with the number of repetition. So for example, as you can see on the top table on the right column, you can see that we have 24 comma 4. This means that we have 5 repetitions of 24, right? So by this method, I could improve the compression ratio for some parameters such as frequency data, such as voltage data. I'll show you the results in the next slide. So we evaluated Draco and simulated data and real data collected from University of Manchester campus 6.6 kilovolt substations. In this experiment, we considered voltage, current, and frequency data. And this is only because their characteristic of these 3 types of data are different. For example, the variation in voltage are less, whereas variation in current are much more substantial. You know, they have a higher rate of changes usually, and also the rate of change in frequency data is very, very low unless some problem happen in electricity grid. So our data reduction algorithm, both Draco 1 and Draco 2, perform differently on these 3 types of data. But as you can see in this graph, we could achieve between 70% to 99% compression efficiency for all 3 types of data. We have also compared Draco with some other data compression algorithm to make sure we are on the right track. We also evaluated the effect of different data acquisition rate on Draco and realized that we can actually achieve better compression ratio for a higher acquisition rate. With this result, we established that when data are being sampled at a faster rate, then the correlation between each 2 consecutive values is higher, and Draco performs best on the data with stronger correlations. So basically, we could collect a huge amount of data, but only transmit a small portion of it, and we could exactly rebuild the original data on the receiver side. So that was a very interesting result again. And we also evaluated the effect of different bit rates on Draco, and we realized that when there are fewer spikes and minimum changes between consecutive data, the data transfer rate is low, right? And then on the other hand, when there is a big change in the data value and when the data variation is high, we observe the higher transfer rate of data. So as you can see in the result in the 2 ringed part corresponding to areas where minimum and maximum change happen. Finally, if you are interested in these sorts of challenges, you can download our journal paper. And I have to say that this paper was selected as the featured article by the editor of the journal based on the quality and impact of the research. So if you are interested in these types of challenge, I hope you would enjoy reading it. Okay. Well, now in the rest of this webinar, I'm going to discuss cybersecurity challenges and some of our works around this challenge. As we all know, smart energy systems are integration of information and communication network, which is the cyber layer, and the energy network, which is the physical layer. While this integration, can offer advantage for us, like helping to decarbonize the grid or increase the flexibility, as we discussed earlier. But we know, on the other hand, this integration of cyber and physical layer would make our energy network more vulnerable to cyber attacks. And cybersecurity is really growing concern for a successful and sustainable implementation of smart energy systems. And the problem with our energy system currently is twofold. On one hand, there is these systems are built upon existing power grid protocols with a number of known vulnerabilities. For example, IEC 61850 has its own vulnerabilities, and etc. On the other hand, the coupling of new communication network to the energy grid would make our energy system again more sustainable, more cyber attack could happen on these systems because of this new integration. So usually these coupled cyber and physical integration can introduce more doors for hackers to get into the system and to compromise our data or listen to the communication and etc. The first question that usually people ask me is, why would anyone want to hack into an energy network? And isn't it more interesting to hack a banking system or a hospital or some other critical national infrastructures? So to answer those types of questions, here are some of the incentives for hackers. Why would they be interested to hack into the system is to take control of utility provider. Sometimes they want to manipulate the market or ransom the energy network, or convey mistrust between people and government, or disturb the balance between demand and supply, and so on. So these are some incentives for hackers, and why would they want to hack into an energy network? Now, what are the cybersecurity goals, and how would they apply to energy system? NIST identified 3 cybersecurity goals, which are called CIA. C stands for confidentiality, I stands for integrity, and A stands for availability. So here is an example of availability attack for you. Availability is making sure the information is available in a timely manner. So for example, if we have a denial of service attack or a jamming attack, these are attacks on the availability. In this example, we can see a smart meter sending its data to DCC data communication company linking smart meter to energy supplier, and we have a hacker sitting in between this conversation. So for example, when smart meter sends load reading message to DCC, the message will be dropped or delayed by adversary, and DCC will not receive the message in a timely manner, and this is an example of jamming attack, and it can compromise the availability of the energy system. The next example is the integrity attack, which is trusting the information that is flowing between different entities. Example of integrity attack is like data injection attack or message modification attack. And for example, when smart meters, this example shows a smart meter sending load reading message to DCC again, and adversary will modify the message. The adversary can inject fictitious message in order to, portray increase or decrease energy consumption for different reasons. So this can be a message modification attack, and this can compromise the integrity of the system. The final example is the confidentiality attack. Confidentiality is only about data is only accessible by authorized users. So for example, when a smart meter sends load reading message to DCC, and adversary could listen to the traffic traveling over the network and could access the message and maybe, modify the message to report incorrect information, again, for different reasons, for example, increase or decrease energy consumption to portray that. And this can be an eavesdropping attack and can compromise the confidentiality of our energy system. The three cybersecurity goals that we discussed in the previous slide can affect most of the communication infrastructure within the energy network. We have a number of different communication infrastructure at various levels of the energy system. Some of these networks, which we are all familiar with, are SCADA system, AMI system, customer energy management system, EV charging infrastructure, and each of these infrastructure has their own challenges, vulnerabilities, and security concerns, which are different from another infrastructure. So for example, SCADA systems are vulnerable to cyber attacks due to a number of reasons. For example, one is they lack active network monitoring or traffic monitoring, and they have weak authentication process. So another example is customer energy management system. The security concern for this system is usually around customer privacy issues and use of public communication systems such as internet. Or for example, the security concern for AMI system is very different. It's because some part of AMI network operate on low bandwidth technology, let's say Wi-Fi or Zigbee technology, and some other parts of AMI network operate on high bandwidth technology, especially where high volume of traffic is expected. And this could result in security concern in terms of communication throughput. And for the EV charging infrastructure, cybersecurity concern, I will discuss in the later slides. Okay, well, until now, a number of cyber attacks or cyber incidents happened on the legacy energy system, right? And there are some, in this slide, there are some of the most famous attacks or incidents that affected our energy sector. I'm not going through these attacks because of time, but we have published a book chapter about cybersecurity concerns for smart energy system, in which we discuss these attacks in detail. And if you are interested, you can download the book chapter and go through that book chapter. All right. In 2050, I spent a one-year secondment with DFT and BASE working on cybersecurity for EV charging stations. I was mostly involved in a number of different projects around EV charging infrastructure that I'm going to discuss in the later slides. One of the projects that I was involved was in collaboration with PA Consulting, and the aim of this project was to conduct a cybersecurity risk assessment and recommend risk mitigation techniques for IoT devices, specifically for energy system. During the PA work, it was found that the risks for EV charging stations in 2020 was low, but it could materialize in 2025. So, and this is because, you know, a number of devices such as EV smart charging, which are connected to the internet, will increase by 2025, and this will cause medium to high risk of cyber attack on energy network. So we understand when the number of smart energy devices, including EV charge points and associated smart energy platform, increase, the cybersecurity risk will increase, the cybersecurity risk will grow too. So for example, one of the main risks that was identified by the PI team was the ability of a large number of smart energy devices to be switched on or off at the same time, which this would cause, you know, large power swing on the electricity network. And then some of the mitigation techniques proposed by PA was to tackle these risks, was to improve security and awareness, provide standard and guidance, provide testing and certification, and also provide legislation and regulations. Another project that I was involved was EVHS, Electric Vehicle Home Charge Scheme. This EVHS is a grant provided by OZEV, Office of Zero Electric Vehicles, designed to offer an additional incentive for drivers. So EV manufacturers who wish to apply for authorization for charge point under EVHS should confirm they comply with EVHS technical specifications. Right. In terms of cybersecurity specifications, also require charge point to be accessed by using the open charge point protocols, OCPP version 1.6 and above, and OCPP is a communication protocol for EV charging station. So during my time at DFT, I assessed how many EVHS grant applications were likely meeting or not complying with the requirements of cybersecurity, and if the applications are considering similar level of cybersecurity measures provided in OCPP. And then I provided a set of questions and recommendations for future use by EVHS team. I recommended some specific changes to be made to the scheme, which were considered by the government. Okay. So now let's see what is OCPP. In EV charging ecosystem, we have two categories of communication protocols. The first category provide communication between EV and the charging station. These are such as IEC 61851, ISO 15118, SHA-DEMO, etc. The second category provide communication between EV charging station and the management system. These protocols are such as OpenADR, IEEE 2030 EEBus, and of course OCPP. Now let's see what are the security considerations of OCPP and if they are prepared to defend against cyber attacks. The reason I chose, OCPP is that it's one of the popular protocols, and it's been currently in use by some EV charging manufacturers, and also UK government require charge points to operate with OCPP version 1.6 and above. So basically, this is the reason I choose to talk about OCPP. So OCPP is an application protocol that provides secure communication between EV charging stations and charging station management system, we call it CSMS, that controls the charging station. And it's reassuring for all of us to know that OCPP development team have considered acceptable amount of cybersecurity measures in their recent version, not very recent version, OCPP version 0.2 and above, they are secure. So these security considerations for OCPP are usually designed around having TLS and public key cryptography using X.509 certificate. And these security considerations are one of the main reasons UK government requires charging station to operate with OCPP or have similar level of cybersecurity if they're going to choose another protocol. So OCPP was designed with 4 main security considerations, right? These security objectives are to provide a secure communication between EV charging station and CSMS, and to achieve this, they propose to use strong cryptographic measure to protect integrity and confidentiality of the messages traveling through this channel. OCPP should enable mutual authentication between charging station and CSMS. Both of these two actors should be able to identify the identity of the other party they're talking to. OCPP should offer a secure firmware update, and finally, it should allow for logging of security events. OCPP supports 3 security profiles. The first profile offers a low level of security, and it should only be used when we have a trusted network. For example, where we have VPN connection between CSMS and charging station, then that's okay to go for the first profile. The second and third profile have improved security measures comparing to the first profile. The second and third profile, they both offer communication security between charge point and CSMS by using TLS. In both of these profiles, CSMS authenticate itself using TLS server certificate. The difference between, the difference between second and third profile is that charging is in the charging station authentication. In the second profile, charging station authenticate itself using HTTP basic authentication, but in the third profile, the CSMS authenticate itself using the TLS client certificate. I would skip this slide because of time. So, in May 2021, BSI published 2 standards for energy smart appliances, which are called PAS 8078 and 8079, and I have contributed to the development of these 2 PASs through my secondment with the government. The PAS 8078 is for energy smart appliances, ESA, and PAS 8079 is for demand side response framework. One key thing to remember here is that ESA, smart energy appliances, is going to be aggregated and connected to the grid, and it can, pose risk to critical national infrastructure. And this is because they can affect loads in large volume. So this is very important. So, and because of this CNI risk, the security needs to go beyond only IoT security, and we call it IoE cybersecurity consideration. But we need to note that the security requirements should be proportionate to the risks. And there should be a balance between security, affordability, and the business need. And that's why we think the BSI process is so valuable, because it gathered information. And view of industry, and they could provide this balance. They could understand where the balance should sit. Now now I'm going to give a brief flavor of some of the approaches of cybersecurity in these passes. There are three players in pass 8078 and 8079. They are smart. They are energy smart appliances, ESA, customer energy manager, and DSRSP, DSR service provider. And ESA is like EV charging stations, battery storage, HVAC, these types of devices that can modulate or shift electricity consumption. SIM or customer energy manager is a logical entity that, or physical entity actually, that can deal with flexibility information, and DSRSP is DSR service provider. So now we have three parts for cybersecurity considerations of these three players. The first part is we want to have verified actors operating in our environment, which is the SRSP. So we need to make sure the SRSP is verified actor. The second part is that we need to secure our asset, which is ESA, like our EV charging station, HVAC, and the SIM. And finally, the third part is to have secure communication between ESA and SIM, so and also between SIM and the SRSP. So the messages need to be secured by authentication and encryption. At Newcastle University, we also look into some other projects around cybersecurity, like cyber interdependency and how to mitigate cyber attacks in smart metering infrastructures. And these works were carried out in 2017 and 2018. Although these are not our recent work, but some of our concepts and challenges are still valid. So just in case, if you're interested, I add the link to the papers that we published, so you can go through them if you are interested. And finally, we need to consider that it's not all about protecting the physical and cyber side of energy sector, but human factor can also play an important role here. And we believe that human factor is the weakest link when protecting the critical national infrastructure. So this research that I would like to share with you, they investigate the disinformation attack, and that was very interesting. So again, if you are interested, you can follow the reference here and have a look at this research, which was very interesting for us. Anyway, before I close this presentation, I would like to share that currently we are doing some collaborative work around cybersecurity with Energy Systems Catapult. One of our work is around proposing a new digitalized licensing regime, and we have provided two examples of how cybersecurity should be implemented in this framework. Another work would be around identifying cybersecurity challenges for digital twins and proposing mitigation techniques to address the challenges of cybersecurity in these systems. So stay tuned for some more results in the next couple of months. Now I will give the floor to Mohammed to present his work around building energy management in digitalized energy system. So over to you, Mohammed.
Hello, everyone. Sorry, can you see my screen?
Yes, I can see your screen.
Yeah, that's great. Thank you. So thanks, everyone. My name is Mohammed Khalil, and I am PhD student at the Newcastle University, supervised by Professor Sarah Walker, Dr. Stephen Makov, and Dr. Zoya Pourmirza. And today I'm going to talk to you about my research, which is like machine learning and deep learning with application to building energy management system. So first of all, let's start with an overview of the project, which is like we will go through first of all about like the key research question of my research and objective, followed by the research strategies and methodologies. So my research, the main theme of my research are two parts, which like in terms of the application, I'm focusing in the building energy management system, and in terms of the methodology, I'm focusing on data-driven method with particular focus in machine learning and deep learning model architect. And in the right-hand side, which is like the building, which is like the urban science building, which is like our team are working on. So why I'm interested in building? There are many different reasons, and the main reason, basically, the building sector, uh, the global contribution from the building sector toward the global energy consumption has increased recently, reaching figure around 36% recently, and 40% of associated carbon dioxide emission. Therefore, there is still Therefore, this fact demonstrates that there is still a huge need to get accurate forecast of the future energy need, of the future energy demand of the building, which like the essence foundation to reduce the energy waste and make the building more energy efficient. So the key research question of my research are four. So first one, which is like, how does transfer learning, we will come through that later in the slide, accelerate the learning process across multiple occupancy prediction tasks where the amount of training data for machine learning and deep learning are limited. And the second research question, how does multitask learning can be used to solve multiple building energy forecasting tasks at the same time, and then compare the results of multitask learning with local forecasting model. And the last research question, how global sensitivity analysis can examine the influence of the input feature on the black box model for forecasting building energy consumption. So, and the main research objective to that, first one, which like to develop a transfer learning framework to predict the occupancy profile. Second one, which like to develop a multitask learning approach to forecast the day ahead of forecast of building energy consumption for either for a group of building or like different type of load within the building. And the last one, which like the experimental study of the uh, to see the impact of the input feature on the output model using a global sensitivity analysis approach. So let's start with research question one. So which like how we can predict the future energy profile of given space or room uh, in a smart building. So in this experiment, we use it data from an educational building, which is like the urban science building. You will use it non-intrusive environmental data, such as like temperature, relative humidity, wind disposition, whatever. So, and the main methodology we have using, which like transfer learning. So basically, the foundation idea of transfer learning, the knowledge, the neural network that has learned from one task, it can be applied and transferred to different tasks. And as you can see here on the figure 4 on the right hand side, as you can see, for instance, a neural network, it has been applied for in building A to predict the occupancy profile, which this building, it has like complex environment of sensor or like a lot of training data. And then the learning knowledge, it can be transferred to building 2, which does not have like energy monitoring platform, or like it has less complex environment in terms of the sensors. And let's start with the model development. We have chosen two neural network architects, which is like the traditional multi-layer perceptron and the LSTM. And the reason for that, we need to examine what is the difference between network architect, such as like long short-term memory that considers the temporal dependencies and order in time series data, and other architects such as like multi-layer perceptron, which that ignore the temporal dependencies. As you can see here on this slide, the key finding, which like transfer learning is powerful framework for the occupancy prediction task in an educational building, and which like it can be extended in the future for to domestic building. Transfer learning could significantly simplify the development of deep learning model, especially when it comes to hyperparameter optimization, since you can like optimize your hyperparameter on the source model, and then you don't need to optimize your hyperparameter on all the different tasks. Which, and the last finding, which like it was expected, LSTM has achieved more accuracy in comparison to multi-layer perceptron. As you can see here on table 1 and table 2, LSTM has achieved we did a lot of case study. This is one of the case study. So LSTM has achieved accuracy approximately 95%, while multi-layer perceptron has achieved accuracy 89%. And in terms of the importance of the transferred layer, we found that the transfer, all the layers on the base model has achieved accuracy, which like it can be that referred to like high level of layer. It contain more like a high level of representation of the feature space in the training model. So the second research question, which is like short term They had building load forecasting, which like in this case we are interested in short term because short term is the essential foundation in a building energy management system to enable different tasks such as like control optimization, enable flexibility between the building and the grid. And my problem it focused like on point forecasting. It's not like probabilistic load forecasting. And in short term load forecasting, there is like two kind of model: univariate, multivariate. My problem it focused more on multivariate model. So basically, I'm interested to predict the energy load considering additional features such as like outdoor meteorological feature and like daytime index and whatever. And here is one interesting observation during our review to the literature. We found that in the year from 2000, in the literature of data-driven method for forecasting building energy consumption. So we found that in the year from 2015 to 2018, there is the study has been used at machine learning. Machine learning has been used much more frequently in the study in comparison to statistical analysis and deep learning, while in 2019, 2020, deep learning it has been used much more frequently than statistical analysis and machine learning. And we believe that one of the reason, like a lot of companies and like in industrial energy industry, they give the access to the open data such as like Energy System Catapult or like Western Pole distribution or whatever. So, and in terms of the methodology, we are trying to do to address the short-term load forecasting, which is like the multitask learning. So the main definition of multitask learning is uh, it's a learning technique. It can be used to solve and optimize multiple associated tasks with each other by a shared model. So let's speak about it has been used like in different domains such as like computer vision, natural language processing, but we will speak that at the moment in this presentation about the energy consumption. For instance, imagine if you have like a group of building, like 10 building or 20 building, and we need to predict the forecasting model to predict the future demand for each of them. And so basically by the end of the day, in the traditional way, in the single task learning, we will end up building like 10 individual model or 20 individual model to predict the future load for each of them, as you can see here in the left hand side in figure 8. While in multitask learning, the situation is different. So basically we can take the full time series data from the whole building and we push that to the shared model, so we can forecast the future demand for all the building in one model instead of building 10 model, which like it can save a lot of time in terms of like hyperparameter optimization, and it can result as well in improved generalization because at the model in deep multitask learning share the weights and parameter across the network. In terms of the architect at the moment, which is like it's under experiment, in multitask learning, I have decided to go with like the encoder decoder, which like it's a foundation and many sequence problem and like machine translation. So the high level definition of encoder decoder is two part. So the first part, which is like the encoder, which like it take the time series data and to present the time series data as like vector representation, and that after that the decoder it can take this representation and generate the output. Like for instance, as you can see here on the in figure 10, like for instance, like that simplified encoder decoder model. Like for instance, imagine like if x1, x2, x3 is to represent the last 3 hours of the day, which like I can tell my model, here's the last 3 hours of the energy load of the building. Can you predict for me the next 2 hours? Which like for anybody working in short-term forecasting, like encoder decoder is like powerful model for the people working like on recursive multi-step forecasting. So in terms of
Okay,
the
Mohammed, just a couple more minutes really left. Thanks. Just so we've got
yes.
time for questions.
Okay, thanks, Stephen. So here's a proposed model architect, like which is like I need to push the whole data to the encoder, which like the encoder can learn the representation from the whole sequence, and then the decoder I can specify the task specific layer, and the last thing I'm trying to do in my PhD in the third year, in the next year in my PhD, which like the third year, which like the global sensitivity analysis, which like I'm interested to see what is the impact of the input feature on the model of future energy demand, such as what is the impact of outdoor temperature or like outdoor relative humidity or like the mean energy demand on the future energy demand. And there is two approach: local sensitivity analysis and global sensitivity analysis, but we are trying to explore more the global sensitivity analysis of the global feature space of the models. That's the end of my presentation. Thank you. And please, if you have any question, feel free to contact me either on my university website or like my LinkedIn page. Thank you.
Brilliant. Thank you very much. So a big, broad range of topics there on everything. Just a quick thing. There's a question to have the links from the that we shared earlier in the chat would be great. Although I think it was the YouTube ones particularly. But actually, I think we'll be sharing the slides from this later, so we'll share that to anyone registered. So yeah, a couple of questions first, and I've got a couple myself. This is to Zoya. Samuel Young asks, is the Draco algorithm dependent on the time series having fixed sampling rates?
Yeah, so can I reply to the first question about the links? So I assume that Liz was asking about the links to the papers. I was not sure. So just in case, if the links is only available for academic use, I'm happy to email the articles. So if you can email me, I can forward you the articles. So just in case if it's not like available. For the second question around the Draco, so I have to say that Draco is dependent on the correlation between data, between consecutive data. So it's dependent on the data acquisition rate. So because when we capture data with higher frequency, the correlation between consecutive data is higher, right? So it shows the stronger correlation, and Draco performs best on the data with stronger correlation. So basically, as we capture data with higher frequency, we are expecting to send larger volume of data, right? But it's not happening. The interesting part is that as we capture data with higher frequency, the volume of data is going to be, the raw data is larger. But when we implement Draco, our data reduction algorithm on this large volume of data, actually we will discard a lot of data, and we will only transmit small portion of it. And on the other side, which is the receiver side, we can rebuild the data exactly as it was in the first place. So we are not going to miss any data or lose any data. We have actually two types of data reduction algorithm. One is lossless data reduction, the other one is lossy data reduction. And in this case, we choose to go for lossless data reduction just in order to not miss any data.
Thank you very much.
Yeah, I hope that's helpful.
Robbie Morrison asks about, so in Germany, indoor heating will be rationed coercively this coming winter. So can smart building systems help here, in relation to also the needs and the fairness? I guess this could be to both of you as well, really.
In Germany, indoor heating will be
the sort of, if there's scarce, energy and obviously very expensive energy becoming, could a smart building system help here, but also ensure that, there is, the people who need that sort of, energy are getting it, the vulnerable are getting it, and, it's also fair.
I think, yeah, smart building system definitely can be useful, but if we have the right technology in place. So if we have, let's say, smart energy appliances, and if the communication is there, that can be helpful, definitely. But again, for some low income residential homes where some of these technologies are expensive, for example, having heat pump is very expensive, things like that, then I guess what would be helpful in those cases is to go for some innovative business model, like having these devices as a service. For example, having like heat as a service, having a heat pump as you would the household would only lease it. and they're not paying for the, for the device in advance, and they only pay for the energy that they use and for the service that they are using. So in that cases, I think smart technology generally is very useful. But again, it's down to many other factors as well.
New models. Samuel Young asks again, is there an open source implementation of Draco available?
Yes, it is available in GitHub. So
great. If you have a code, it'd be great to share that as well. Robbie Morrison mentioned much of Germany's on district heating. Just last couple of questions. I've got a quick one for each of you here, actually, before you go. Just going back to the cybersecurity thing, Zoya. How long did it take with some of those examples you showed to discover there was a cyber attack and then respond to them? And sort of then how do they get incorporated into sort of new protocols and maybe, implementing them?
How long that it took?
Yeah, or the whole process from when you discover it, when you sort of see if it's a new sort of type of attack, how you update some of the protocols and how they get sort of, what determines what is upgraded, really.
Sure. So, for example, I can give you the example of working with DFT and BASE over in 2020. So it took us around a year to work with the PA consulting for identifying where are the vulnerabilities of some of the devices. And actually, we cannot select all the devices. So we have to be very selective on choosing. For example, we are considering energy storage, we are considering HVAC, we are considering smart meters, and for example, EV charging stations. So we should be very selective, and then that selection would be on the impact that they have on the grid. So we have to first prioritize what component we are considering, and then considering that component in a whole system. So we cannot only consider one component, for example, smart meter on its own, because this is a whole system. So we need to understand how, for example, smart meter is operating, how DCC is operating, and how the supplier is operating. And so DCC is doing lots of, let's say, authentication and routing and anonymization. So so understanding this whole process only for few components at least would take around a year. And we only provided recommendation for policy and recommendation for government. So I myself was not involved in implementing, these recommendations into the, let's say, protocols. But again, for the workaround past 8078 and 8079, it was like a good few months. Yeah, I guess for the BSI team itself, it was around a year maybe. So yeah, it's not a very quick process. I won't say that we can do all this in like 2-3 months. It's definitely much more than that.
Thank you very much. Last question, Mohammed. I've wanted to transfer learnings or the multitask sort of learning here. I'm wondering how much it matters that you, within the learning process, you actually group buildings together. So, if you had a school, say, or a sort of a pub or a church, I mean, is it better to try and apply the learnings you do on a certain type of building and then apply them to the same type of building? Or, is there, has there been much studies into that?
Yeah, basically, like in the terms of the transfer learning for the occupancy prediction, basically the available data we have studied at the moment, because the only data it's like in the urban sites building. So basically, we did a lot of case studies. So basically, some of them we applied, for instance, in the source like model, we applied like, for instance, it's office space, which is like it has a small size, and after that we transfer it, for instance, like to teaching space, which like it has like different business function, which like, and even like a regular business hour to see like what is the impact of that, and even like with that's in terms of the transfer learning. And in terms of the multitask learning, like when I need to predict the future energy demand for building, at the moment I'm doing the experiment for the multi-load, which like lighting, heat pumps and stuff. But in the next step, I need to do that for the domestic building. So basically, I need to experiment that like in group of building together, which like the main that probably I need to explore probably or no, it's Akron project from the power distribution network, which like it's a smart meter data from London, which like it has 1,100 home. So basically, my idea at the moment, I need to cluster the energy profile and of the building and push that to the system. One of the idea, but here like it's like really you have one interesting question, you present one interesting question. So basically, for instance, like in multitask learning, how we can, for instance, merge like domestic building in addition to like commercial building together. So that's like really interesting question. Yeah, thanks, Steve.
Fine. Well, thank you very much, both Zoya and Mohammed. So this video will be available shortly after we finish up here, and we'll share around your contact details and slides as well, so anyone can contact you if they have further questions. So thank you very much, and yeah, it was great to hear your talk today.
Thanks, Steve.
Thank you.
Thank you.
Bye.
Bye. Bye-bye.